Imagine flying at the speed of sound, high above enemy territory, and having to release a weapon so precisely that even a few milliseconds of error could send it crashing back into your own aircraft. Or worse, missing the target by a football field's length. Welcome to the world of modern aerial bombing, a world where gravity alone just doesn't cut it anymore, where physics, engineering, and precision guidance systems come together in a deadly ballet to ensure that bombs don't just fall, but fly, glide, and even think. Today, we're diving deep into why modern aircraft don't drop bombs. They eject them, the rise of smart munitions, and how technology turned aerial bombing from a blind gamble into a surgical strike. Why bombs aren't just dropped anymore. During World War II, bombers like the B-17 would fly in formation, at high altitude, opening bomb bay doors and letting gravity do the rest. The bombs would simply fall. That was the entire system. But modern military jets are much faster, often flying at supersonic speeds and much lower altitudes. Dropping a bomb in this environment is not as straightforward as it sounds. When a bomb is released from a high-speed aircraft, it doesn't just fall down. In fact, due to air pressure and turbulence under the plane's fuselage, there's a real risk the bomb could be sucked back up and strike the aircraft itself, a catastrophic outcome. To prevent that, bombs are no longer simply dropped. They're pushed, kicked, and even ejected with incredible force. The science of separation, how bombs leave the aircraft. Before any bomb is cleared for use, it undergoes rigorous separation testing. These tests simulate how bombs behave when released at various speeds and angles, using wind tunnels, drop pits, and movable mounting systems that replicate real-world flight conditions. Why so much testing? Because premature bomb separation could tear apart a $100 million aircraft and endanger the crew. The goal is to make sure the bomb exits cleanly, clears the plane's body and slipstream, and travels on its intended path. This is where ejection racks come into play. Highly engineered mechanical systems that do two jobs: secure the bomb during flight, forcefully eject it at the right moment using 4-inch pistons or pyrotechnic cartridges. Yes, you heard that right. Many explosions are used to push bombs out of jets at the speed of sound. Pooping bombs, a weird but real thing. So if front ejection is so complicated, why not just push bombs out of the back? Well, that's been tried. The A-5 Vigilante, for example, had a bomb bay between its engines. It literally pooped out nuclear bombs from the rear using explosive charges, buying the jet enough time to escape the blast. This gave rise to the legendary nickname, the Nuke Pooper. More recently, aircraft like the C-130 have been retrofitted with rear and side launch tubes as part of the Harvest Hawk program, turning them into ad hoc bombers. The rear launch tubes let them drop GBU-69 glide bombs, ideal for special operations forces. Some versions even required the crew to wear oxygen masks inside depressurized cabins to make it work. So yes, pooping bombs is still a thing, just smarter now. Dumb bombs become smart. The rise of guided munitions. Dropping bombs accurately was a nightmare during World War II. A B-17 flying at 20,000 feet had less than a 2% chance of hitting a 100-square-foot target. Hundreds of bombers were needed to take out a single bridge, often resulting in widespread civilian casualties. Even during Vietnam, accuracy was dismal. The Thanh Hoa Bridge required 800 bombing runs over 3 years. And then, in 1972, came a game changer. Laser-guided bombs. With just 11 F-4 Phantoms and 24 laser-guided bombs, the bridge was obliterated in a single day. That moment marked the birth of the modern precision strike era. Laser-guided bombs and beyond laser-guided bombs, LGBS, rely on aircraft or ground operators to paint the target with a laser. The bomb then homes in on the reflected laser light. These were precise, with circular error probabilities, CEPs, dropping from 400 feet to just 20 feet. However, lasers don't work in bad weather, so the next revolution came with the JDAM, Joint Direct Attack Munition, a kit that added GPS and inertial guidance to traditional bombs. These work in all weather conditions and have an accuracy of just 16 feet, with a range of up to 45 miles in the extended range version. Cost? just $35,000. Compare that to a $1 million cruise missile, and it's easy to see why smart bombs became the go-to solution. Long range and small size. The evolution continues. For longer range, wings can be added to create glide bombs like the AGM-154 JSOW, which can hit targets from 80 miles away. At the same time, bomb sizes have shrunk. Enter the small diameter bomb, SDB, just 250 pounds, yet capable of surgically striking a target with minimal collateral damage. Aircraft that could carry a single 2,000-pound bomb can now carry 4 SDBs, hitting 4 different targets in a single mission. New versions like the GBU-53 Stormbreaker even track moving targets in any weather, thanks to advanced seekers. Bunker busters, the heavy hitters. But what if the target is underground? That's where bunker busters like the GBU-57 Massive Ordnance Penetrator come in. Weighing 13.6 tons, it's built from Eglin steel, capable of withstanding 193,900 pounds per square inch, over 5 times stronger than the steel used in buildings. They're long, narrow, and use delay fuses to detonate after penetrating up to 200 feet of reinforced concrete. Think of them as high-speed nails that explode only when they've reached deep inside. The countermeasure, fighting bombs with concrete. So how do you stop bunker busters? You can either make the concrete thicker or stronger. Engineers realize that stronger concrete is more efficient. That's why ultra-high-performance concrete, UHPC, is now the standard, reaching 30,000 to 50,000 psi, often with no rebar, just millions of embedded metal fibers. It's a technological arms race. Mechanical engineers build better bombs, civil engineers build better bunkers. And the game goes on. Wrap up and teaser, from poop-shooting nuclear bombs to laser-guided precision strikes. The story of aerial bombing is one of constant innovation, driven by necessity, powered by physics, and perfected by engineering. And the future? It's already here, with AI-powered targeting, hypersonic munitions, and drones carrying out precision strikes autonomously. Want to know how drones are revolutionizing aerial warfare next? Hit that subscribe button and stay tuned for our deep dive into the rise of autonomous aerial weapons, because the sky is no longer the limit.